Assalamu alaikum. So from now onward, we are going to analyze some of the important components, and we will do the mechanism analysis on those. The very first one is about CAM. So during this lecture, we will briefly go over the CAM's different types, characteristics, and with the ultimate goal to analyze CAM and to the construction of its displacement diagrams actually. So basically the designing of the CAM basically. So a CAM is a machine element used to drive another element called a follower. So the purpose of CAM is to drive a follower through a specified motion by direct contact. So CAM and follower mechanisms are simple and inexpensive, have a few moving parts, and occupy very little space. I'm quite sure you have done uh, a, a brief introduction of CAMs and followers, which are when you have done your thermodynamics module. So the working principle of the CAMs are already being discussed. So with this thing in the mind, so I'm not going to spend a lot of time on the basic, but I have some few slides on just introduction of the CAM design. So furthermore, follower motions having almost any desired characteristics are not difficult to design. For these reasons, CAM mechanisms are used extensively in modern machinery. So as I said, you have done most of the time in thermodynamics module. So the working principle of the CAM you might have discussed in the internal combustion engine, but there are many other applications. So I also have very brief overview of those. The versatility and flexibility in the design of CAM systems are among their more attractive features, yet this also leads to a wide variety of shapes and forms and the need for terminology to distinguish them. So because they have quite broader spectrum of applications, the CAMs, so it would be really good to have a brief overview of the terminology so that we can distinguish. So as I said, few slides on the kind of like introductory. So a CAM, a rotating or sliding machine member, which is a CAM, whose function is to impart a predetermined motion to another part, to the follower, right? So rotating or sliding machine member, that would be called as a CAM, whose function is to impart a predetermined. So predetermined means is the specified motion actually to another part follower that rolls or slider along its surface by direct contact. So there are different shapes. This is a very common way of describing CAM and follower. So you see, it's the working principle is quite simple. If you look at these diagrams, so the CAM, this has kind of like oval shape, and it has one of this rod with this particular example has this roller here, small mini roller attached with the follower. So you can imagine when this one rotates, so of course the follower will have reciprocation movement. So in a very simple word, we want our CAM to rotate in such a way, so it is rotating in continuously, but the follower has to do the reciprocation, but of course it's not like a linear reciprocation. So for example, this part, for example, this part, this part, when the follower is at this position, when we go into 90-degree, for example, if this one cam has been rotating for a 90-degree, so it has a maximum position. So you see the follower has traveled this much distance, right? So of course the follower has traveled all the way up here, so it has some certain velocity, certain acceleration, and it has covered some displacement. So at 180, the follower is back to its original position, 270 is back to that position, and in 360 is the back to that position. So from 0 to 90 it goes up, and from 90 to 180 it comes back. So this is the only reciprocation out of 360 we are getting from this classical example. Well, it mentions here by direct dry contact, but internal combustion engine, normally you don't have a dry contact, rather you have the lubrication, proper lubrication present over there. And in this diagram, there are many different cams are shown, because as I said in the very beginning, there are wide variety of applications for the cam. So depending upon the requirement, you can have different designs of cam. Followers are normally more or less similar. Yeah, very slight change in design, but the sole purpose is to do the reciprocation, and this reciprocation can be performed by using some of these cams. All right, so there are different ways. Yeah, so this is very good example in an internal combustion engine. So first of all, the cam shaft, which is shown over here, so this one, so this gets power from the crankshaft. So there is a crankshaft. So crankshaft, where does the power come to the crankshaft? Crankshaft gets the power from the internal combustion engine. So you have the combustion process and you have expansion, so that gets the rotation of crankshaft. So crankshaft is being connected with the camshaft. There are many different ways to transfer this power. For example, if you're doing this with a chain, this is called as a timing chain. If it's done with a belt, you have a timing belt. And in most of new internal combustion engines, this crankshaft and camshaft, they are linked. They could be linked through some gearing applications. So there are many different variations actually, and that's why it is interesting. So now you see how we are performing this function. So the cam has to rotate, so it's rotating this way. So of course the rotation speed will depend on the requirement in the engine. And when it's moving, so when it has the highest point, it gets a push on this tappet, and which is connected with a push rod. So this is a push rod, and then push rod, this is a can connect with a rocker arm, and this end is called as a rocker shaft, this point, and this rocker arm is then connected with directly with the valve, right? And this valve has a valve spring. So of course the purpose of valve spring is to bring back the valve. So when you get a push downward, so it opens the valve. So this space being open, and you have the process of intake or outtake, or the exhaust, and that way you can perform. So the spring gets back to valve to the original position. Of course, there are many different designs. I said this cam can be placed in modern engines directly on top of valve. So here you put, so then you don't need all this assembly where you have tappet, push rod, rocker shaft, and all those. So you can really get push directly by placing cam. So of course you can think about it. If the cam is directly placed over there, so it is more like getting rid of small components which can cause further wear and tear, and of course this is more durable. And the cam is called as overhead cam shaft. So this is a normal typical operation in a camshaft. So the purpose is we have the rotary motion at the cam and the valve is reciprocating. So we are converting from rotary to reciprocation motion. All right, so then you can analyze this cam by doing Groshoff law, which we have done in very first lecture, to investigate how many degree of freedom or what is the mobility of the cam basically. So you see, this is one of the example being discussed here. So what is it? So you have, this is the follower. So this is not a typical cam and follower mechanism. So this is the cam, which is definitely the way it is, like it's an oval shape. And the follower, you can really place follower at any place. You can have the vertically up, down, and anything like that. And so if you analyze, so these are 3 links. So one link is basically the frame. So this is one link, the frame, as we have been doing this, and then you got another link which is a cam, the other link is follower. So we got 3 links. How many J1s? So you got revolute joint, so the rotary joint. So of course when the cam is can only rotate here, so that's why it's a revolute joint. Then another revolute joint is at this follower, so it is revoluting as well. So that's why we have 2 J1, and then we got J2. J2 is the interface actually, right? So you just see why we have J2, because it is roll and slide. So it is sliding because of this principle, because this one is rotating component. So it is rotation as well. So that's why you consider it as a J2. So now if you plug in these numbers in the Groshoff law, and then you have the number of degree of freedom. So we are just doing one kind of mobility, which is the requirement of the cam. So that's the purpose here. So some applications are listed as I explained, an automotive engine to open intake and exhaust valve. So you see this animation. Sorry about the fast speed. That's the best I actually found it. So you see, this is a good example. So this is the crankshaft. It is connected with one of this belt, so belt and pulley system. So that's why it's called as a timing belt. And why we call it timing? Because it is defining the time of open and close of the valves. That's why we call it as a timing belt. And then this one is connected with the cams. The camshaft is connected with cam, and of course this will define when the valve is required to be open and close. So this is the actual figure of one of the cam. So where you have the cam directly sitting on top of the valve. So some other application is hydraulic pump. So this is one of the examples. So you see here cam is of course is a little bit of different. So what we got here, the fluid comes in, and then gets pushed towards this way. So that's the outward. So you are basically pushing the fluid, which is the hydraulic, means the oil, for example, oil pump, typical oil pump, and it is doing the reciprocation mechanism. So we are getting through a very simple. So you see, you just need to make, this is the figure. So you need to make the cam by using uneven surface. Of course, uneven means with the requirement of the designing. And when it causes the push, so at one side it goes backward, in one side it goes forward, and then it gets pushed. So these little mechanism over here is to have the non-return valve. You might know that. So non-return valve means that we are pushing this way, but no fluid can go back actually, because when the spring gets it pushed this way. So this is like a reciprocating pump. There are many different versions of pumps. So this is one of the category of hydraulic pump which works on is reciprocation actually. So in some types of hydraulic pump, this is rotary pump. Yeah. So this is one of the, so the working principle is more or less similar. So here we have 2 different versions actually. You see, one is which is the image is from this one, So you have the inclined plane, so it's a rod, and then this is of equal length for each combination, and it gets pushed, so the oil gets to this way. So you see, so from top to bottom, it is basically, here you have more oil, the space for more oil, and this is less, means it is continuously supplying. So this axial pump with the axial piston rotary pump, uh, this is more like a higher flow rate uh, oil you can provide with using axial piston rotary pump. So there are two different designs basically. So there are two different versions here. We have the combination from here, which is like cam could be this design, or you have like this inclined surface where you have, so you see here the shaft is been at some certain angle, but here you have shaft in a straight and axially. All right, then we have yeah, this is another example with a radial piston. So uh, this animation might not be the best one, but actually you have this slot like that, right? So where these little piston heads, they can move, and the oil is present over here in each subsection. It gets pushed actually. So this has certainly this one of this gadget actually. So this is one of the another example. For example, this one is this one is shows a very good picture of the actual component. So you can imagine, so it goes downward and then opposite upward, and then it gets pushed the oil actually. So this is also when you want a continuous supply of oil actually. All right, then some of the classification of cam and followers. Sometimes cams are classified according to their basic shapes. Figure next slide shows the 4 different types of cams. What are the different cams? So this classification is based on the basic shape of the assembly. So we have a plate cam, also called a disc cam or a radial cam, a wedge cam, a cylindrical cam or a barrel cam, and end cam. So this is the basic shape of the cam. So this classification is based on a basic shape. One by one we'll discuss. So for example, this is a plate cam, also called disc cam. So this is like a disc shape. So when it rotates, so in this classification, we are not considering this part, the follower or radial cam. So this is the typical example which we see actually in automotive application. Then this is a wedge cam, where so we have a linear kind of like cam, and of course when it's sliding, which it shows here, so it gets so as I said, the follower has to perform a job of just reciprocation. So you see with such cam we are able to do that, the linear reciprocation. So this is called a wedge cam. So this is shaped like a wedge actually, so that's why we call it as a wedge cam. Then this is a cylindric cam. Yeah, so this is again discussed, already shown to you. This is like a cylindrical shape or a barrel. So you see the cam has to, so when this one rotates, then you have the reciprocation, right? So the follower actually reciprocates this, which is shown as a y direction. Yeah, so this is one of the end shape. So the end cam or face cam. So again, sorry about this high speed animation actually. So the purpose here is to the follower reciprocation has been done on the face of the cam. So that's why we have up and down movement basically, or reciprocating movement. All right, then we have the basic shape of follower. So that was about cams. So all these 4 classification are based on the cam, and now we have 4 examples where for classification where they are based on a basic shape of the follower. So a very simple one is a knife edge, right? So this is a knife edge. So it's like a sharp edge. So that's why I call it a knife edge follower. And then we have a flat face follower. So this is a flat face. So we are not concerned about the cam here. It's just classification of the follower we are talking about. Roller follower, they are also very common in some of the equipments. So we have roller over here. So you can imagine when you have roller followers, so means this is more like you're reducing the friction basically, because knife or flat surface is just pure sliding. So this was is rolling. So you reduce the frictional losses. Then we have a spheric face or curved shoe follower. So this is curved shoe. This particular example where you have it's moving, and this is like a spheric shape. So it's not a circular basically. It's more like a half a sphere. All right, then we have cam displacement diagram. So during the rotation of a cam through one cycle, the follower executes a series of events. Yeah, so this is important to understand basically how the follower is being operated. So during the rotation of a cam through one cycle, so one cycle means it is covering 360 degree, right? The follower executes a series of events as demonstrated in a graphic form in the displacement diagram as shown below. So this is a graphic diagram. So in such diagram, the abscissa represents one cycle. So this abscissa, so this one is 0 to 360. So this is 360, one cycle, one rotation. Input usually one revolution of the cam, and is drawn to any convenient scale. So because if there are different sizes of the cam, so the best one would be, so if you're drawing on a white page, then you need to choose some good scale that represents 360 degree, and then you can plot it actually. So we will do some plotting, so you will get more confident on how we do that. The ordinate represents the forward travel. So we got this one. So this one from here to here, this is the forward travel. So this much, how much follower can lift. So you see when it says over here, so that's the lift. So this is the maximum follower distance can travel or reciprocates. For a reciprocating follower is usually drawn at full scale to help in the layout of the cam. So normally you draw a full scale for the follower, because follower has to cover very small distance. So that's why we just try to draw as much as basically as like the actual conditions. All right. On a displacement diagram, it is possible to identify a portion of the graph called rise. So if you think about it, this is the portion is called as a rise. So follower is moving upward, covering a distance of the lift. So starting from 0, when it has no lift, the reference position, and it's going upward, right? So this is the portion where the follower has rise. So this is called as a rise, where the displacement of the follower is away from the cam center. So from here to here, this is the part where the follower has traveled away from the cam center. So it is the one where it's reciprocating, basically it's going upward. Then the total rise is called the lift. So that's why it's called as a lift. So the maximum rise is called lift. The return is the portion in which the displacement of the follower is towards the cam center, and portion of the cycle during which the follower is at rest is called dwells. So this one is called as a dwell. So this is the point where cam as the follower is not moving actually. So it reaches that maximum position, cam is continuously rotating. So we start from here. So for example, we start from here, cam rotates. So you got, for example, cam here is like so you got circular, and then you got the profile, and the follower is over there. So follower starts traveling. So when it reaches this position, so basically we are, so if this is the cam base circle, we will do the terminology. So this is like the portion which is the up here, and then you got the maximum lift. And during that portion, because it's like more circular, so that's why we got, this is the dwell basically. And then it has to return. So it's not necessary the way it goes up or the way it goes down is same. No, it's not true, because it really depends on the timing. If let's say we want to move the follower up slowly and return fastly, because it depends on the engine operation, so that would define what should the slope actually. So we got one dwell over here, which is like after rise, there is a dwell part where the cam actually has to stay. Sorry, so this is the cam stays at one of the position, then it's returning, and then it's a dwell point portion where the cam is the closest to the cam center, the follower. All right, so we have some fundamental terminology for cams. So the figure shows a radial cam with reciprocating roller follower. So this is the diagram where you have so what we have. So we can show the radial cam with reciprocating roller forward. The forward terms are important in order to draw the cam profile. So this is the follower. This part is the follower, and the cam which is being shown, the blue line, the outer blue line, that's the actual cam profile, right? So some things are being extended just to draw those terminologies. So what you actually see, so what actually you see is this part. So that's the cam, right? So that's the cam you see, that actually you notice. And then this is the follower. So these are the components which you observe, but what you have more than that. First thing is about base circle. It is the smallest circle that can be drawn to the cam profile. This is the smallest circle. So if you see here, so this one is the cam shaft. So this is the cam shaft. This has the key. You know, we use keys for the shaft so that we have rigid fixation. So that's the cam shaft. And then this is this circle, right? So you see this circle is touching at this position, the minimum position, to the follower. So this is the minimum circle, which is called as a base circle. You can draw for a cam. Then we have a trace point. So it is a reference point. So basically, so the trace point is, yeah, so that's the center of this follower. This is called as a trace point because it will be the one which is traces. So it is a reference point on which the follower and is used to generate the pitch curve, right? So now this is the point which is actually plotting this circle. So this circle is called, so this circle is called as a, right? So when the cam is moving, so cam is moving, so you draw, this is the circle you draw, basically pitch curve, basically which draws the pitch curve basically. So we draw the pitch curve. So this is, just remember, this is called as a pitch curve and this is called as a pitch circle. So we are interested in pitch curve because this is the point which actually drawing the pitch curve. So this one, this line. In case of a knife edge follower, the knife edge represents the trace point, right? So because it's a roller, so this is a different aspect, but if it's a knife edge, then this is the point which traces out the knife, the edge of the knife basically. corresponds to the cam profile. Yeah. So you just imagine if this is the knife edge, it will touching at this point, right? So when it's touching this point, so then you are actually drawing the cam profile. So you don't have the pitch curve when you're talking about knife edge follower. In a roller forward, the center of the roller represents the trace point, as like here. So center of the roller, that's the point which draws the pitch curve. Okay, then we have pressure angle, one of the important parameter. What is this angle? So it is the angle between the direction of the follower motion and in normal. So which is shown over here. So this is the point basically where we want to draw the pressure angle basically. So what is it basically? So you got, this is the follower motion, right? Follower is always upward, right? So when is this one is moving, so this is the point where the follower is always on that direction. So we got the direction of the follower motion and a normal to the pitch curve, and this is the normal. So this is the normal on the pitch curve. So that's the pitch curve we have already known. So you know the normal is basically which is at 90 degree basically. So when you have one tangent and one normal, so this is normal. So the angle again, so this is the normal on pitch curve. So pitch curve is being explained over here. So this the outer one is a pitch curve. So the normal on any point. So this is the point where you have the normal and then the follower motion, because follower is always, when let's say this point comes, travels here and comes here, so the follower is still upward. So it is always linear. This is follower motion is always upward basically. So the angle between them is called the pressure angle. This angle is very important in designing a cam profile. If the pressure angle is too large, a reciprocating follower will jam in its bearing. So you see why the term is pressure angle is associated here. So why we are calling pressure angle basically. Just imagine. So this is the point where when it comes here, so when it travels here, so when cam is traveling this way, so this point reaches over here. So this is the point where cam, where the follower will start really highest motion upward. So this is the point where the follower is doing its highest position movement. So it start to rise as quickly as possible at this point. So for example, when this cam, the way it has been drawn for this one, traveling from here to here, when cam comes from here to here, so it is a slow progression upward. So it is slowly going up, but actual climbing is starting from here. So this is the point where it's starting here. So now imagine if you have this angle is highest, all right? So highest means it is really high. So you need, because we are giving quite peaky mountain to the follower. So follower has to do a lot of work to climb up on this follower is cam profile. So if this angle is large, so what does it mean? You have, the follower has to go quite straight, like you can imagine if the slope is low, so it is easy to climb, but if the slope is high, then it's difficult to climb. So if the angle is, you have designed the cam, if the angle is really high, there is always possibility that the reciprocation follower will jam in its bearing, so it will not operate, so because it's unable to go up or climb up. So that's why this pressure angle is quite important. And now this pressure angle, what this depends on, this is basically depends on the pitch curve, which I said is quite important thing, because pitch curve is if it is that way, that it has the really high angle or low angle. So this will define the angle actually, right? And then continuation, we have the pitch point. So it is a point on the pitch curve having the maximum pressure angle. So during the pitch curve on any position, you will have one certain point where you will have maximum pressure angle. So here, as I said, shown here, so this is the point where you have the highest pressure angle, because pressure angle will keep changing throughout the cam movement. So this is the highest pressure. So that's why it's called as a pitch point. Then we have a pitch circle. So it is a circle drawn from the center of the cam through the pitch point. So now you draw another circle from pitch point. So from here to here, you draw a circle. So this one, this is called as a pitch circle. So this is shown. So this is one complete circle. Then pitch curve is already been explained. So it's the curve generated by the trace point as follower move relative to the cam. For a knife edge follower, the pitch curve and the cam profile are the same, whereas the, yeah, so this has already been explained in last slide. Then we have a prime circle. So it is the smallest circle that can be drawn from the center of cam and tangent to the pitch curve. So now, so this is the prime circle. So this is the prime circle, right? So this is the trace point. So this is this one as it shows. This one is prime circle. Right. So what it says, it is the smallest circle that can be drawn from the center of the cam and tangent to the pitch curve. So tangent to the pitch curve is this one basically. So this one. So this is the tangent. This line. This is the tangent on the pitch curve. So you draw a circle. This is called as a prime circle. For a knife edge and flat face follower, the prime circle and the base circle are identical. Yeah. So because this one is touching the base, so that's why they will be the same in knife edge and flat face follower. For in roller, we have this much distance basically. For roller forward, the prime circle is the larger than the base circle by a radius of the roller. Yeah, so you can imagine, because this is the point where you have the radius of the circle of the follower. So lift or stroke, which is shown over here. So this is the maximum which travels the follower. So it is the maximum travel of the follower from its lowest position to the topmost position. So that's the maximum travel you can have. All right, so very briefly, so displacement, velocity, and acceleration for a cam design. The displacement, velocity, and acceleration diagram when a knife edge follower moves with uniform velocity is shown in figure ABC. So these three diagrams shows displacement, velocity, and acceleration. So as explained earlier, so in the displacement what we have, so when the follower displaces from A to B, so it goes up, it rises up, it reaches to B1, that's the maximum position, it stays on B1 to C1, that's the dwell point, that's what we call dwell, and it comes back, that's the return, so that's why it's coming back closer to the cam, and that's again another dwell. So this is one dwell, this is another dwell, and this whole shows a one revolution of the cam, right? So this is the angular displacement. So angular means one revolution is being shown complete. So this is like one revolution from A to E. So the abscissa represents the time, the number of the seconds required for the cam to complete one revolution, and or it may represent the angular displacement. You can plot the same thing on time, because if you know the angular speed, you can work out what will be the time. So on abscissa, you can have time and as well as the angular displacement. Most of the time we will do the angular displacement in form of angles. We will not plot with time, but of course you can do that. The ordinate, as shown, is represents the displacement or velocity or acceleration of the follower. Since the follower moves with uniform velocity, so this one is a straight line. What does this mean? The slope, as you see, the displacement, and this one, if you plot, so if it's going continuously up, so it means it is going with a continuous speed, so with a constant speed. So that's why during that time your velocity will be a straight line like that. So it's a maximum velocity we achieve, and that will remain constant during the rise. Then during the dwell, it will be zero velocity because follower is not moving. And then you have on the return another constant velocity because it's coming back towards cam. The follower is coming back towards cam with a constant speed. So that's why it shows a negative speed, but it's not really. So it's a magnitude is sometimes, if let's say you have forward and return is the same, so the velocity magnitude would be same as well. And then we have another dwell. Then we have acceleration. So acceleration, so it explains on the next slide. So here it shows a maximum acceleration values. So infinite acceleration. So you got like infinite acceleration over here. So when it's coming back, it's infinite acceleration, decrease, deceleration, infinite deceleration, and then infinite acceleration basically. Yeah, so in other words, AB1 and C1D. So AB1 and C1D must be a straight line. A little consideration will show that the follower remains at rest during part of the cam portion. So here, the follower is on rest. Here, the follower is rest. The periods during which the follower remains at rest is known as dwell, as shown by B1, C1. So B1, C1 is one dwell, and DE is another dwell. From C, the figure C, basically, we see that the acceleration or retardation of the follower are at the beginning and end of the each stroke is infinite. Why it is infinite? This is due to the fact that the follower is required to start from rest and has to gain a velocity with no time. So you see, this diagram is only drawn from the velocity. So you see at 0, we had 0 velocity, and with no time, it achieved a maximum velocity, which was the design velocity. So means if within no time something goes up with such a velocity, it will certainly has a infinite acceleration. Yeah. So this velocity diagram requires to be changed because this is not practically possible. Because again, so the velocity shows from 0, within the 0's time, you got immediate increase in velocity. That can only be possible if you have infinite acceleration, or same thing with the retardation as well. So when it's going down, deceleration. So this is only possible if the acceleration or retardation at the beginning and at the end of the each stroke is infinite. These conditions are, however, impracticable. So this is not true. So we'll just modify a little bit this diagram. So what is it? Yeah. So in order to have acceleration and retardation within the finite limits, it is necessary to modify the conditions which govern the motion of followers, right? So we'll just modify the conditions. This may be done by rounding off sharp corners. So you are rounding off the sharp corners of the displacement diagram. So you see we are here rounding it off on each point. So we are just not sharp decline or increase. So it's like transition at the beginning and end of each stroke as shown in figure A. By doing so, the velocity of profile, the follower, increases gradually to maximum. So you see, now this is more true. So velocity from here, 0 to, let's say this is 5 meters per second. So from 0 to 5 meters per second, it has gone in increments like 1, 2, 3, 4. This is more realistic approach. So the velocity goes up slowly, goes down slowly for the rise in the dwell 0. And same thing goes in the return stroke as well. So it decreases and then stays some value and then. So now this is more realistic. So we got some constant acceleration. So during this velocity, when it's going high, so you have some certain acceleration. because I hope you have done a lot of problems like that in dynamics and other subjects, where you calculate from the velocity, you calculate the acceleration. So if you have a constant acceleration, you can achieve maximum velocity like that. And same goes with the deceleration or retardation as well. So the modified displacement, velocity and acceleration diagram are shown figure. The round corner displacement diagrams are usually parabolic profile, because the parabolic motion results in a very low acceleration of the follower for a given stroke and cam speed. So most of the time it is parabolic profile, this rounding off, right? Yeah. So one more thing which is very good. So I found one of very interesting animation. So a follower. So this is the process of showing the follower. So follower actually is doing reciprocation. So it's going up and down. And during this up and down movement, of course, if you want to see, this is more like a simple harmonic motion. So this shows a simple harmonic motion, which can be plotted as a sine curve, cos curve, for example. So this is like a sinusoidal curve is showing. So when it's reciprocating anything, when you have a system of spring and mass, for example, you have done some analysis. When it's reciprocating, the system can be represented as a simple harmonic motion. So now from onward, we will use this terminology. The follower, when it is reciprocating, it is basically doing some sinusoidal or simple harmonic motion, right? So we are going to use this terminology onward. All right, so we continue with that one with the next lecture. Thank you.